Welcome back, everybody. With this session, we get to pick up with Standard 5, or as we think about our mathematical practices, we begin on with Standard 5, looking at how kids and how we use tools strategically, both as we teach math, but especially in terms of our students, how they're using tools. Of course, one of the first things, or maybe it's not of course, but a lot of times one of the first things we think about when we're talking about using tools strategically with our students, or having our students use tools strategically is, well, what tools are they going to use, right? And then why and when is it important to use those tools? So if we were together, we might brainstorm a list of tools like rulers and maybe even a compass or protractor. A lot of times the first thing that comes to mind is a calculator and those pieces, and those are certainly all tools, right? But tools are more broadly defined if we really look at how students use tools and what this practice is meant to address, and that is in saying that tools are anything that a student is going to use to perform a task. So things like base 10 blocks are a tool, right? Connecting cubes, hundreds grids, grid paper, number lines, hundreds charts, even their pencil and paper and mental math is a tool, right? Those are all tools that help kids perform the tasks that we give them and tasks that they come across. So as we think about all these things, we want to make sure that whatever the tool is, or however we're working with our kids, it's about helping them realize that sometimes there are supports out there that can help us to access the math. And ultimately, we want them as the learner to know how to pick the right tool, when to use the hundreds chart, when to use their calculator, those kind of things. So let's take a look at those things here in this practice. Also, keeping in mind that there are times when we're going to need more than one tool, right? Or where a task, especially a really good task, is going to require multiple tools to be able to go through it. So let's think about these mathematical statements or pieces and think about what tool would you use? Now, if we were together, what I would do is I would assign you guys each a tool, and so we would give somebody a calculator, one group a calculator, give one group graph paper, we'd give one group, they're only allowed to use mental math, one group, so all those pieces, and we'd say, okay, you have to use your tool to solve your task, and let's think about each of these. So since we are not together in that way, we are going to look at these and instead say, what tool would I use, and would some not make sense? So for like this first one, 5 times 6, while especially early on using grid paper might make good sense, later on it might not make sense. Maybe mental math is the tool that I'm going to choose to use, right? How about 23 times 15? Again, imagine that if you had the calculator, all of a sudden you might feel like, yes, now I want to use the calculator, where number one, I wouldn't. If I might want to use grid paper, but a protractor or a compass might not have much use for me in that case. If I was doing a task like this or this, let me pull up a few of these here for us. And just looking at those various tasks, what would you think about having a variety of tools or having the wrong tools in front of you, right? Because what we also know is if we're using certain tools with kids, they will want to use those tools all the time. So how do we get kids to use those tools right? So let's think in the same structure that we've used in the first part of this. Let's look at certain pieces like a number line, like broken rulers, or taking an inch and magnifying it out. Thinking about mental math, like how do we get kids to work together and or use number partners? How do I think in my head, right? And so as we go into those, let's keep these two things in mind. Again, the page references here are in reference to the putting the mathematical practices book that we looked at in the very first session, or the first session of this PD. So ultimately, we want kids to make a choice to choose a tool that makes sense for that particular task, and then to decide which tool is the most efficient. And knowing that kids aren't innately going to know what the tools do, so we have to teach them that the different tools have different powers. So using number lines being one of those powerful tools for helping with computation, and especially with estimation, right? So being able to look at something like a number line and view the quantity on it gives us a chance to make some comparisons, right? Like this whole idea is, which is it closer to, and we see these with our benchmark fractions like 0, 1/2, or a whole, and we say, well, where is 1/6 closer to? So the student using that number line is certainly the appropriate tool, or is an appropriate tool here. Broken rulers can be an appropriate tool to understand the purpose of the tool, right? We see these kind of tasks, and often we might wonder, like, why would we use a broken ruler? Why wouldn't we just use the whole ruler? And I guess the point here is that oftentimes in a number line, we're starting at a place other than 0. And oftentimes when we're using a ruler, kids don't start at the right place to begin with. So rulers can certainly be a tool that kids are going to use, right? So how do we help kids develop their own rulers, right? And I'm sure many of you have done tasks where you have kids fold a piece of paper, right, like this. We're going to fold it in half. We're going to open it. We're going to mark that as a half. And let's talk about this is like an extended inch or an extended foot. In this case, let's think about it as an extended inch, right? And now we're going to refold that, and then we're going to fold it in half again. So now we have fourths. And let's talk about what does that look like in this kind of blown up version on your piece of paper. So that we're starting to construct these ideas about a ruler, like, are all the sections equal? Do the labels make sense? Where would 0 be? And why would it be where it is? Why is it on that piece of paper? Obviously the 0 is going to be on the edge, right? But on every ruler, that's not necessarily where the 0 is. And then where is a hole? So if I folded this piece of paper, well, the length of that paper might be considered a hole, but kids might not see that right off the bat. And then why do we see now, once we folded it twice, that half and 2/4 are in the same place? So as we continue to do that, we continue to build this idea of ruler and measurement and fractions, and being able to construct my own tool, and building into these ideas that we take on in math throughout, like these questions propose here. So another strategy when it comes to this standard, right, is looking at number partners or mental math, right? So we're going to take this task, right, and the task is to find a number partner that makes 10, right? So we give you something like this, and we say, okay, so now find the number partner that's going to help make a 10. We can certainly make this more or less complex, right? You could just have kids identify one set of number partners, or we could put fewer numbers in the box, right? We could put numbers in there that don't have partners, right? So there are some that just wouldn't fit together. So we can do this certainly with young kids as they're learning tens, but even with our older students, even with maybe even our 4th or 5th grade students, not just the struggling students, but kids who may just have lost that sense of making tenness, and that making tens is a huge part of mental math. Right? So then we start considering with kids, right, like, when does it make sense to use mental math, and when does it make sense to use paper and pencil? And one thing we might want to do ourselves is to think about, when would you want to use a paper and pencil? When would you like to use mental math? So it makes me think about, like, that first problem, well, I'm definitely going to want to use paper, pencil, or a calculator would even be better. But that second one, I may choose that mental math is going to be a lot quicker, right? Because if I know Well, 60 times 4 is 240, and 4 times 3, right, is going to be 12, and 240 and 12 is going to be 252. Well, that's probably faster than me writing it down and solving it. Again, those things that we do are all a result of many iterations of practicing mental math and thinking about the 10ness of 60 and 3 more. And those kind of things don't just naturally happen. They happen because of number talks and some of those pieces that we can work through over time, right? But ultimately, we can help kids realize that mental math is a strategy and it's also a tool that can help us throughout our lives, right? So ultimately with this practice, what do we want kids to be able to do, right? We want them, if we model the tools, if we model number talks and we include kids in number talks, if we show kids the use of rulers and allow them to work with them, ultimately we're helping kids be able to effectively choose a tool and then use that tool. If we're helping familiarize our kids with a variety of tools, right? If we're showing kids why we choose a certain strategy or a certain tool, and we talk about and show and explore, probably even better than talk about or show, but explore the limitations of certain tools and the advantages of other tools, then that helps kids be able to make good judgments about what tools they're going to use. And that takes us through our fifth math practice and brings us into attending to precision. And attending to precision is one of those pieces that I think from an outsider, non-educator perspective is one that people think that's what math is. And it certainly is a huge part of math, right, is being precise, but it's not all that we do in math. So what does it mean to attend to precision, right? And why is it important? What does it mean to be precise? When is precision really the most important? And then how do we help kids communicate precisely, right? How do we get there? Let's look at some strategies here that we'll go through with attending to precision, looking at estimates versus exactness, right? And then ways to build precision with vocabulary, such as those listed there. And we'll go through those here in just a second. So let's think about estimate or exact, right? When is real precision important and to what degree, or what degree of preciseness isn't important? So we think about proposing a variety of scenarios to kids, and of course this isn't on just one day, but over time, right? So if you're buying bags of candy to put in treat bags for your birthday party or something like that, do you count or do you make sure that you have exactly the right number of pieces of candy, or is it an about? Right? If we're measuring the dimensions of a doorway to put in a new door, is it important to be precise, or is it okay for that door to have gaps? If we're buying pizzas for our class party, might depend on who's paying, who decides whether this is an estimate or exact, but you kind of see like this is one that there's an exactness, there's a certain degree of precision that matters, and then there's a certain amount that, well, we do just want to make sure we have enough, but we also don't want to have a ton. If we're buying carpeting or painting, those kind of things, the exactness and the precision gets to become even more of a discussion. So having kids come up with those scenarios and discussing when do we want to be exact and when do we not really care is important. So exactness and precision, or attending to precision, right, is also a function of estimation. Many will contend, or some people will contend, that estimating is actually, in many ways, that estimation oftentimes is more difficult than actually doing the actual problem itself, because estimation requires us to know something about how the numbers work together. So it may engage a different part of the mind, which is exactly what we want to do in math, right? So will the sum of 8 and 7 be greater than or less than 20, right? And thinking about, well, how do kids think about that? But can we see how this degree of estimation, it brings in an element of precision, but not exactness, right? So if two numbers that are less than 10 are added together, are we going to get the value of 20? Those kind of things. Is the difference of 81 and 29 closer to 40, 50, or 60? So again, we're forcing that discussion with kids, right, of now we've closed the gap on precision a little bit more. Is the sum of a third and 4/8 greater than or less than 2? This one feels a lot more like the first one. Well, got less than a half, got half and less than a half. Is that going to be more than or less than 2? But then if I start closing that in, right, with if I'm working with older kids, greater than or less than 1, greater than or less than 3/4, all of a sudden now the degree of precision becomes more and more important. And then finally, how would you estimate the product of 2 and 4/10 and 63? Would the product be between 2 times 60 and 3 times 60? Why or why not? And again, estimation being a way to pull kids into precision that can certainly vary, right? We saw word web earlier with one of our math practices. And so we can use word webs here as well as a really quick way to look at math ideas and to focus in on math vocabulary. So one thing with precision is with number values. Another thing that's so important in math, of course, is using precise language. So if we throw a word in there, like choose rectangle, for example, right? We could put rectangle in there and then talk about what is that precise enough for this, right? Is rectangle precise enough for some task that we're doing? We could talk about definitions. We could talk about connected words. We could use, instead of a word, we could use a phrase, right? Like, can you give me an example of some math concept, right? And we could connect it to other things that we know. Another way to get into precision, or a different way to look at precision, is by sorting and labeling. We can look at things like this and talk about how kids can identify similarities and differences between concepts. We can, if we were together, we would certainly do this with some cards, right? So we see that first one: sum, minus, join, compare, subtract, add, take away, apart, plus. And how are those related? Are they opposites? Are some of them opposites? Are they always opposites? What kind of problems could we build off of those? And then, like, skipping down to the third one there: square, trapezoid, hexagon, rectangle, rhombus, triangle, pentagon. We get into those discussions about squares and rectangles and all of our different quadrilaterals, but especially, when is a square a rectangle? When is a rectangle a square? Is a square always a rectangle? Is a rectangle always a square? All those pieces about precision of language become very important as we work through this. So another strategy is mystery words, right? So in mystery words, we're going to give every pair of students a set of word cards. So we got these word cards, right? And we're going to have partners take turns picking a card at random. The student describes the word. So I pick a card. I'm going to describe it, right, without actually saying the word. So you can think of some popular games that are out there that use the same strategy. And then the partner's trying to figure out the word from the clues. So I've got to be precise in my language as I'm describing this thing, but I can't be so precise that I give away the exact word, right? And we're going to get these words in. And again, this can be something that's set up both as a game. It could be a center. It could be just tasks at my desk, right? So we throw words in there the kids are going to have to think through. Then we get into this idea of precision within building equations or number sentences. And so translate the symbol, right, becomes part of this. So if I have a phrase such as this, right, so $4.10 is greater than $4.05. How would I translate that? How do I use the correct symbols? How does a mathematician write that sentence? This might be how I read it, but then how do I write it? 1/4 of 16 is 4. or doubling a number and then adding 6 more. So you think about those and translating those into number sentences versus this, right? And again, these aren't the same. These are not the same, concept or the same tasks, right? But if we compare those two in terms of which is more challenging, well, it'd be interesting if we were sitting together, right, and trying to decide which of those is harder to read, which of those is harder to make sense of, and then working through that. This could certainly be done with some matching cards, right? And so we could have kids try to match what they think makes sense there. Another, this one is titled Word Boxes, right? We could certainly call this a Frayer model or something similar like that, where we give kids a chance to be precise both with their definitions and thinking about what not only what is the definition, but what is my definition, and then thinking about what does it look like, where do I find it in the world, what are other words. One of what I think is often used in a Frayer model is example and then non-examples, which can be very powerful as well. So let's look at one student's sample here. So I'll give you a second to read through that. So as you look through that, this is again just being how one student interpreted symmetry, right? And we can think about the importance of using student examples and student definitions over necessarily what the book says. So then we get into integers or something that's maybe a little more advanced concept. And again, we get this peek into how the student is really thinking about it. Seen some teachers use this strategy in as building student dictionaries or math dictionaries, and then kind of focusing in or posting some of the ones that are maybe the best or the most interesting. And again, the power here being that these are student words, student examples. And ultimately, when we're talking about precision, what are we really shooting for, right? We, as the teachers, we have to model precise communication, right, by using appropriate vocabulary. And again, vocabulary may grow over the years, but it shouldn't change, right? So my definition of a square should always be the definition of a square, right? The examples we use a lot of times are that, a rectangle is not too long and too short. Because when we do those things and we try to make things easier for kids, we ultimately make them harder, right? So let's define things based on precise vocabulary. And so as we as teachers continue to refine what we do, we're looking at how do we give kids a chance to write about math, to talk about math, and then to guide students into using really precise language so that in the end, kids are communicating using clear definitions and they're saying really what the mathematics is, but also in their own terms. And that kids understand that how symbols are used, and symbols including our numbers, right? And that then brings us up to our 7th mathematical practice, right, which is looking for making use of structure. This one is one that on the surface level looking at it, I kind of think, what are we talking about here? So let's kind of explore that one a little bit, and let's think about this in terms of patterns. We know that there are an awful lot of patterns in our number system, some that we see really easily and some that are a little more that we may not discover as quickly, and some that we won't discover if we're shown shortcuts, right? So a lot of times we miss kind of the beauty of the number system or the power of the number system when we're shown the shortcuts, right? And then how do we help students make sense of that? So let's take a look at this and see, can we find the pattern in something like this? So we might or might not see a vertical pattern here, right? As we continue to cut in halves, right? So I might recognize that, 0.25 is half of 0.5. I might not as quickly recognize that 0.125 is half of that, but I do see that there's something going on with denominators, all right? 1/2, 1/4, 1/8, 1/16. So it seems like something is going on with denominators, and they seem to be doubling, right? And in the second column again, the denominators seem to be doubling, and in the third column, the denominators seem to be doubling, again with a vertical pattern. And that might help me think a little differently if you ask me about, well, what is the decimal equivalent of 1/6? My first temptation might be to go back to how I was taught, right? It might be to say, well, divide 1 by 6. Well, I could probably have thought of that as, if I know what 1/3 is, and that's 0.33, and we know it's repeating, but 0.33, well, it's half of that, right? So what is half of 33? Well, that's between 16 and 17, so it must be about 0.16 or something like that. So this whole standard is looking at structure, right, and looking at how that helps us make sense of problems. So if I have an open-ended question like this, right, there are 10 kids at a party, how many are boys, how many are girls, that becomes kind of this open-ended task, right? We're assuming, or maybe we assume that there are boys and there are girls, but it doesn't say that, right? So what are all the possibilities? So as we work with kids, think about, well, how do I structure that in a way that the kids can see that these are the possible options. It's always fun to me as we work with kids, or as I get the chances to work with kids, they'll start with something like, well, 5 and 5. Okay, well then how else could it be? 1 and 9. And it becomes this very random task, right? And that's totally natural, right? We all do that as learners, right? Our first attempt at a problem is to go to what we know, right? And as we work with kids and as we work in the mathematics and we look at making use of a structure, then we start saying, okay, so those are a couple possibilities. How would we put this in a way that I can see all those options, right? So we can look at this in so many different ways, right? So any way that we can get into patterning is a way to get into helping kids build a structure to keep track of how many options or how long it's going to be, or what ultimately, how does this turn into an algebraic statement, right? Because usually that's where these ultimately go, right? So something like this, if there were a row of 50 connected equilateral triangles, what would the perimeter measure? So I've got to come up with something here in terms of, well, how many sides do I get each time, and every time I add a triangle. And so thinking through that and having us as adult learners and student learners kind of work through a task like that forces us to think about structure, or it becomes very random again. And we know that randomness is not the way we normally work through mathematics. Then we also look at building flexibility, right? So if I have something that looks like this, right, there were 1.5 cupcakes left on the plate, and Liam and Molly decided they would eat them. How much might each person have eaten? And thinking about that as, again, this is a slightly more advanced version, right, of the first task we looked at, with 10 kids being invited to the party, and some boys and some girls. But now we've got 1.5 cupcakes left. So thinking through that, it becomes a little bit more cognitively demanding because of the numbers that we're using. So ultimately, we're looking at can students decompose 1.5? So how many different ways can I make 1.5? Well, we know there's an infinite number of ways. So just think through that for a second, right? Think about how would you solve it and how do you think some of your kids would solve it? And then think about how could you make this an accessible task for somebody who maybe is struggling or still emerging? And how could you make this a more challenging task for students who need the challenge? Or if I was in a unit on, say, fractions or decomposing whole numbers into fractional parts, how could I make this more demanding for those kids? So it makes me think it would be so good to have your discussion in on this too. And that, again, maybe one of the follow-up pieces that we ask you to do in this assignment. But it makes me think about, well, the vast majority of people, probably kids too, but are going to start with something like, well, if there's 1.5 cupcakes left, a lot of kids are going to say, well, one on one plate there's one, and on the other plate there's a half. But then we go back to what was the question asking? The question was asking how much did each person eat, right? So this really is about how much do we start with, right? Not how are we going to break up 1.5, unless we think of it as, well, sorry, now I'm misreading the question. So it says Liam and Molly decided they would eat them. So my bad. So rewind for a second. I'd taken myself down a weird road. But so if I have this 1.5, we are working to decompose that 1.5. Then I can see that I'm going to have kids who say, I'm going to eat one, and Liam's going to eat one, Molly's going to eat a half a cupcake, and that's an easy way to break those two things up. So how do I push kids beyond that, right? And say, well, you need to have at least two fractions. Maybe if I really want to make it more demanding, I'm going to ask in those two fractions, they need to have different denominators. And so, we can push this to create the need to be flexible, right, with the numbers. So how do we ultimately get there? So let's look at pattern cover-up. Let's look at our patterns in our hundreds chart. Let's look at ratio tables. Let's look at number lines. So pattern cover-up maybe looks something like this, right? And so I've got these numbers, and I say, okay, so what's the pattern? Is there any way to know what the pattern is? And at this point, is there any way? I don't think, unless we're just really good, like Wheel of Fortune champion kind of people, to really think about that. So what if I know that? Now can I determine the pattern? And I might be able to start guessing, or I know there's 7 numbers in between there, and all those pieces. What if I know that? Now can I figure out the pattern? And we might have some kids who say, yeah, I got it, right? I can figure I've got it. And then you say, okay, does that change or does that affirm your pattern, your prediction? Yeah, these are certainly better in small groups than they are in a whole class. So now I've got something different maybe than I initially thought. And then ultimately, does your pattern work? And what would the next 3 numbers be, or what would the 10th number be? So pattern cover-up is kind of just a fun, not just a fun, it is a fun way to get into recognizing the patterns in number sequences. And then we have on our hundreds charts, right? So when we look at a hundreds chart, another way to getting into repeated reasoning or structure, I guess I should say, recognizing structure, Do kids see the horizontal patterns? Do they see the vertical patterns? And a lot of times we've done a lot of work with those. And then do we see the diagonal pattern? And a number chart like this, always be careful that we're using a chart that begins with 1 and not with 0. That'll change the pattern a little bit, and this is certainly the direction we want it to look like. Until we get into the multiplication charts, right? And so in a multiplication chart, we're going to start with our zeros but we're going to make sure the whole first row and the whole first column are zeros. And of course, that's a different structure than a hundreds board. And in a hundreds chart, right, do we see vertical and horizontal patterns? Do we see diagonal patterns? And can we talk about those, right? Can we talk about this as a horizontal pattern, right, as we go across, that we're counting by threes? Can we see the horizontal pattern of the fours? And then do we recognize that those are equivalent fractions, right? That 3/4, if I look at because when I multiply 3/4 by 1/1, right, in this case I'm going to get 3/4, right? And when I multiply by 2/2, I get 6/8. And when I multiply it by 3/3, and really exploring, like, this is a really good place to bring in that idea of another form of 1, or a convenient form of 1, right? That anytime I multiply by 1, I get the same value. So if I start with a fraction of 3/4, I can use my multiplication chart to explore that, right? And so that all those equivalent fractions are there, right? And it also works, of course, for if I did 3/5, right? I can start with the column, or sorry, the row of 3 and the row of 5, and I see 3/5 is equivalent to 6/10, and that's equivalent to 9/15. And so again, and why that works is not a mystery, and it's not magic, right? It's because I'm multiplying by both the top and the bottom numerator and denominator by the same value, and when I do that, I'm multiplying by a form of 1, right? I'm multiplying by 2/2 or 3/3, and that's just 1. What about diagonally? Do we see the pattern, or can kids see the pattern as we go diagonally? And this being an interesting place, especially as we get with older kids, to look at some growing patterns, right? Why does that increase by +3, and then +5, and then +7, and then +9? What's going on there in terms of how numbers work? So I'll leave that one up to you to explore that a little bit more. Ratio tables, again, another way to get into looking at structure. So Margot was painting flowers on a mural. Every flower had 3 leaves. How many leaves were painted? How many leaves were on the mural after 7 flowers had been painted? Again, lots of information, really hard to mentally kind of hold on to all that information. And so we start teaching a structure, right? So, all right, if I had 1 flower, how many leaves do I have? If I had 2 flowers, if I had 3 flowers, if I had 4 flowers, and now I can get up to 7, or some kids may recognize the pattern and say, well, it's just times 3, but it's a little tricky to see that because the number 3, the multiplier, is actually in the problem, right? It's not there. It's not necessarily what kids would do if they were writing it out. And it also, by forcing it into the ratio table, we're really pushing kids into the structure they're going to need as they hit middle school and even into algebraic thinking, right? Without getting into all those nuanced details of what the math is doing here. But this is really important that we're recognizing it's not just counting by 3, we're counting by 3 because we're talking about the flowers, right, and how many flowers we have. So we could then look at how numbers work when 2 pieces of data are connected, and that's really what a ratio table is. Really, ratio tables can really support kids as they're learning about multiplication and division. These can be done early on in the process. Kids don't need to be recognizing the pattern so much early on, but later we're going to guide them to hopefully seeing those patterns, and hopefully they recognize those patterns on their own at some point too. So looking at questions like this kind of force that need, right? One more strategy with recognizing structure is looking at number lines, right? We know in our standards that number lines are referenced quite often, and that's because number lines are a structure that kids need to be able to use, and it's a structure that always works, right? So when I'm adding, can I see how the number line works? When I'm multiplying, do I see how the number line works? Can I see why, like the example there that these two examples, why the order of the numbers in addition and multiplication, why the commutative property works the way it does, and how they represent different things, but they end up in the same values. So ultimately, we as teachers are giving kids investigations, right? We're guiding discussions. We're helping kids recognize why properties work the way they do. And we're asking kids to come up with their arguments by modeling how we come up with arguments to prove mathematics. And then ultimately we want kids to understand properties and not just say that's the commutative property or that's the associative property or that's multiplying by 3. And it's that I understand the process of all that. And then truly, and I think we've seen this in the organization of our standards here over the last few years better than maybe we did in the past, is the importance of being able to be flexible with numbers, right? To be able to compose and decompose numbers, to be able to do that with fractions as well as counting numbers, because that ability to break numbers apart really helps us do mental math as well as just really making sense of what's going on. And that brings us to our final mathematics standard or practice, mathematical practice, and that is looking for and expressing regularity and repeated reasoning. And a lot of what we just did in Standard 7 or some of that could certainly be interpreted here too. So these certainly are not meant to be, well, I'm practicing. We don't just practice Standard 7, right? It brings in all the other areas. And so as we're looking at, or we're exploring regularity and repeated reasoning, we want kids to recognize what's going on with repetition and then figure out why is that happening? Like what's going on? Because again, this one goes back to making that overarching standard of making sense in problem solving. And that is that we expect it to make sense, right? So how can I recognize this repetition? And then when I think about repeated reasoning, what kind of things do we think about as learners, and what do we want our kids to think about? So what are some strategies to get us there? So here are 4: exploring repetition, finding shortcuts, organizing and displaying data, and then classroom investigation. So let's take a look at some of those. Let's start with exploring repetition, right? So those of you who work with or have worked with young kids, and probably all of us who have worked in elementary, right, we look at what happens when I'm adding 1 to a value, right? Like early on, that's a connection piece, right? Oh, well, when I'm adding 1, it's like counting 1 more, right? It's moving up 1 on the number line. Those are, obviously some of the conclusions that we have, but our kids aren't innately going to have that, right? So as we explore repetition, right, what does that look like as we get a little bit further up in our thinking, right? So we take a task like this, right? We're looking to figure out what is our rule for multiplying by 10, obviously, as opposed to when I multiply by 10, just add 0 to the end. But what is a rule for multiplying by 10, and why does it work that way, right? So we're going to roll a die or a number cube to see how many ladybugs landed on your leaf and how many spots are there. So I roll this die and I get 6, or I roll 2 die if you want to do it that way to get to the bigger numbers, and I get 8. And so if I say there are 10 spots on each one, well then how many? And so we do this a number of times, or the kids are doing this a number of times. We can certainly change the structure, but ultimately we're doing something that's causing them to multiply by 10, and we've given them a structure, right? So we've given them the values here to start to see, well, what's going on there? Like, why is 3 times 10 30 and 4 times 10 40? And does that help me multiply by 10? And then as we move along, if I know what multiplying by 10 is, then I can extend that into multiplying by 20, right? And I can extend that into multiplying by 11 or 12, because if we recognize that multiplying by 10 does this rule, right, And if I do one more set, then that gets me multiplying by 11, or two more sets gets me multiplying by 12. So it's not just about multiplying by 10. And sometimes that's where we miss the opportunity when we're teaching kids a rule, like just add a 0 to the end. Well, that doesn't work when I multiply by 12, right? But if I understand how multiplying by 10 works, truly, then I can work on to finding other shortcuts or other kind of student-driven rules, right? So that was exploring repetition. Another way is really looking at certain investigations, or giving kids specific tasks that are going to lead them to develop their own rules, right? So we don't want kids to memorize math rules without understanding them, right? There are certainly tricks that'll make math easier, but there really is no trick in the math, right? The trick should be my rule as the student or the learner. Once I understand the math, then I can make better sense of it. So if I look at a task like this, I'm asking kids things like, what do you notice? Do you see a pattern? Do you notice anything interesting in the solution? Versus a trick, right? So as I'm asking those questions and kids are sharing, they're hearing each other's thinking. But again, investigations to find shortcuts versus let me give you the shortcut, because once I give you the shortcut, it's really hard to get you to think about the mathematics. Once I understand the what we might perceive as the easy way is really kind of cutting kids off in their long-term understanding. And the reason we know that is because we end up having to teach those shortcuts again and again and again and again, and they're never really the students. And a lot of times those shortcuts break down over time anyway. So what's another way to get kids into this last mathematical practice? And that is similar to what we did previously here, right, is organizing our data into a table so that we can see the pattern, and ultimately so that kids can see what's really going on here, right? So we want to make sure that we're giving kids a problem that challenges them to extend a pattern and look for generalizations, relationships. So as I look at something like that, and then I look at a similar word problem, right? Alice jumps ropes faster than anybody else in her class. She can jump rope 8 times in 4 seconds. How long will it take her to jump 40 times? You and I might look at that and say, well, it's 8 times 5, right? It will give me 40, so it's going to take her 20 seconds. But that's the result of doing a lot of these repeated reasoning tasks, right? So it's, well, if I can do it this many times in this amount of time, how do I extend that? And then how do I kind of prove that? How do I justify my answer? When we are doing these kind of things, it's really important that we make sure that kids discover these math rules, right? We want to give kids that opportunity to say, I get it, right? And so doing classroom investigations, right, is one way to do that, right? And so an example of this that we've seen used in different classrooms is the survey of the week, where you might assign each student or pairs or trios of students to come up with survey questions. So they develop a survey question each week, and they go around and collect data on that. So it might be something as simple as, fourth graders' favorite flavor of ice cream. So they go and they gather that data. They and maybe the whole class works on compiling that data, maybe in one way, maybe in a variety of ways, and then discussing it and sharing out what kind of things they see. It could be numerical data, right? Like how far the average fifth grader can jump. And so they get, you do a representative sample of fifth graders, or they have the whole class jump, or they have 5 kids from each fifth grade class jump. And so we're giving kids this opportunity to learn how to ask their questions. We're giving them a chance to gather real data and then to interpret that data and maybe make some suggestions about it. Structured in some ways by the teacher, but then also in some ways that just leaves it a little bit more open-ended. And so what are we really looking for in this final math practice? And what are we going to do as the teachers, right? We're going to ask kids to really look for patterns, to expect things to make sense. Ask them, what do they notice? Do they see patterns? Because we want kids to recognize that repetition is pretty common in mathematics. We want kids to think about how their new problems are like other problems that they've done before, that we're not just giving them random math tasks, but that math builds on previous understandings. Because again, we want kids to recognize that if I used this strategy earlier, I might be able to use it here. And then ultimately, we want to make sure that we're setting up investigations so that kids discover shortcuts, that kids create generalizations. And we're going to certainly guide them in that process, but we're going to make sure we really want the generalizations and the rules to come from the kids' thinking. And so as we kind of close this up, I just throw a couple pieces at you, right? Like some of these kind of things, right? 3 different veterinarians each help a total of 63 dogs and cats in a week, but each of the veterinarians helps a different number of dogs and cats. How many dogs and cats could each veterinarian have helped? Using tangrams, right? Lots of tangrams out there, looking at how we put pieces together to create a whole might be one example of how we do that. And then we build on that, right? So it starts as this kind of hands-on fun task, and then we start asking questions like, well, then what is that quadrilateral that we see? What fractional value is that? And then of the whole tangram, right? Can we find the fractional value of each piece? And ultimately, as we think about the 8 mathematical practices we're really thinking about is how do we structure ourselves and our teaching in our classroom in such a way that it encourages mathematical thinking of all of our students. So again, thank you to NCDPI for providing some of these materials for us, and I look forward to us getting into the articles and the content in our upcoming sessions. And I hope this has added a few things to your toolbox. I hope that as we post the assignment for this, that you'll share back with me and with the group things that made sense to you, things that maybe pushed you, and some things that just affirm the great work that you're doing each and every day. So thanks for what you do, and we will see you either face-to-face or virtually again soon.